Accelerate the speed of simulation studies with automated processes that validate design performance. Solid Edge simulation capabilities provide design engineers with powerful tools to help digitally validate their designs and build better products in less time by front-loading the simulation process. Solid Edge simulation can calculate hydrostatic pressure loads in a linear static or coupled study. This can be used to determine the maximum and minimum pressure that is exerted by a fluid from a given point due to gravity. Running such a study on this tank for a dosing assembly line, we simply need to select the faces the load will be applied to, define a height for the fluid in the tank, and define the material density. In this case, we'll also apply a fixed boundary condition to the bottom of the tank, then mesh and solve the simulation. Here we have a new body mesh option, a new Siemens mesh technology that simplifies and improves the tetrahedral mesh for complex parts with intricate bodies and automatically cleans up small faces and edges. Viewing the results, we can see the areas of higher stress at the bottom of the tank and lower stress at the top. The maximum stress value is nowhere near the yield stress, so the thickness of our tank is more than adequate for the job. Adjusting the level of the material in the tank is as simple as editing the hydrostatic pressure load and selecting a new reference point, or simply adjusting the offset value. Solving the study again allows us to see the differences in pressure that the lower fluid level has on the tank. Next, we'll look at some of the enhancements to simulation studies of structural frame models. As we define this study, we can see that automatic link creation now considers all cases where rigid links need to be created and only creates those needed for the study. We can adjust the connector option to specify a maximum rigid link length to automatically create links, or, as we'll do here, we can use the automatic link command, which enables the model to be set up far more quickly. We'll go ahead and apply a fixed constraint to the bottom of the structural frame and define a force to the top two horizontal beams, then solve the study to see the results. Another new feature for Solid Edge simulation is the ability to view beam von Mises stress plots for frame models. Factor of safety plots have been enhanced and are now based on the von Mises stress, producing far more accurate results than the maximum combined stress results that were used previously. Switching back to the main assembly, we can see there are some pins holding the dosing mechanism in place. Opening one reveals that it's a mesh body. Solid Edge simulation can now validate mesh models resulting from a 3D scan or generative study. Here we can see the results of an existing linear static study. Being able to create the simulation mesh right on top of an existing mesh body truly sets Solid Edge apart. There's no reverse engineering or any other complex procedure required. Simulation-driven design helps designers get immediate feedback on design performance by embedding simulation into the CAD environment and designers' processes. Simulation display performance optimizes load times for results data, making Solid Edge simulation faster than ever before. Offering unique products is a competitive strategy that creates distinctive value, wins more business, and increases customer loyalty. However, manual design customization can be expensive, error-prone, and time-consuming. Completely embedded, the Solid Edge Design Configurator allows you to rapidly design products to customer specification while eliminating expensive errors inherent in manual design customization. This conveyor assembly needs to be customized for different length, width, and pitch values. Since the style and number of connecting plates on the underside are directly related to the size of the conveyor, this assembly cannot simply be controlled by variables alone. However, Solid Edge Design Configurator will easily allow the rules to be created to define a customizable product. The required input parameters can be defined to guide the configuration process. Here, the style and form of input is easily controlled and allows us to choose the desired drop-down menus and checkboxes and control how they will appear in the final configuration form. Values can easily be added for any of the parameters, and images can be included to help the end user identify the needed inputs when configuring the model. Defining a new input parameter for the pitch of the conveyor, we can quickly configure the name, type, label, and render styles to have the input appear as radial buttons. Pitch values for the conveyor can be customized between 60 and 90 millimeters. However, since different lengths of the conveyor require a different pitch, visibility rules need to be defined to configure when each pitch value can be used. This is done by making use of simple expressions to define the intelligence. As we do this, the function can quickly be validated with the built-in validation tool. Functions can also be copied and pasted to reuse them. Skipping to the last configuration step, we can see the configuration form is defined with the necessary picture. and the correct pitch options appear based on length chosen. Defining rules is the next step of the process. There are a variety to choose from, ranging from variable binding to simple expression and truth mapping rules. Here we have multiple rules to drive and configure the connectors at the bottom of the conveyor. In this example, we have simple conditional and expression rules to take the length of the conveyor and determine the number of connectors needed. Then, a truth mapping table is used to decide whether the pitch of the connector is a fixed value or calculated based on a formula. Another rule can then be used to calculate the position of the connectors based on the length input. All rules can be quickly validated. Finally, we can specify the actions that the model is subject to. These can range from replacing a part with an alternative, renaming files, or even saving models in a different format. In this case, we need to replace the roller with a different one, dependent on the width of the conveyor. This makes use of the standard alternate components function in Solid Edge to define the two replacement parts. We'll then set some variable rules connecting our model variables defined in Solid Edge to the functions we set up as global rules in the previous steps. A rename model action will ensure that our final assembly will be renamed appropriately, and also create the other necessary outputs, for example, step files as shown here. The order of these actions can also be easily changed. Once the configuration is complete, we can run it and quickly create as many different custom variants of the conveyor as necessary. Any newly generated configurations can be easily shared with Pack and Go. The configuration logic is all stored within the CAD model. There's no need for further plugins or external resources. Once done, we can see the resulting files of the latest configuration we created, complete with the additional step output. The Solid Edge Design Configurator creates new design iterations at the click of a button, dramatically reducing the development time for creating customized products.